Okay, so now in this example, we're going to do a real live application, and it's a simplified model, but we're going to do a dam. And we're going to assume some things. This is like the Hoover Dam, and this is based on the Hoover Dam, but we're making some assumptions. One is that it's a flat dam. The Hoover Dam is actually an arched dam, so we're making that simplification, if you will. So, but we're going to use this example to show how we can calculate the hydrostatic force on this dam. So now this is also an isosceles trapezoid. So these sides are the same. Okay, these slant sides are the same. Okay, the bottom base is 750 feet. The top base is 1250 feet. And so when Lake Mead is completely full, full, then the height is the depth of it is 530 feet. Usually, when it's completely full, it's about 10 feet below the top of the dam. Okay, so now our reference point in this case is going to start at the top of the dam, right in the center of the dam. Okay, so instead of the surface of the water, we're going to put it at the top of the dam. Okay, so that means that our depth that we're going to use for S of x, or let's call our S of x function, is going to be the value of x minus 10, because we've got these 10 feet here that have no water. So in that case, the actual depth, the real depth, is whatever's measured on this x-axis minus 10 feet. So it's going to be x minus 10. Okay, so that's going to be that function. Now the width function. Okay, so the width function is changing on both sides here. Just very similar to the isosceles triangle. So let's do this. Let's again take our strip. By the way, this is sediment. So this is the bottom. This is underneath the ground, so that's not included. So let's take a strip, a little tiny strip across, and I'm going to also do this. Okay, now I created a triangle here, a right triangle on both sides. So I know, since this is 750 feet, I know this distance up here is 750 feet. And if that's 750 feet, then what's left over? Well, that's going to leave us 500 feet. And so I know this distance here is 250 feet, right? Sorry. So what I'm going to do is I'm going to use similar triangles to try to figure out what this is, because this I'm going to call A. I'm just going to call this side of this smaller triangle A, because what I did was I created similar triangles again. So I'm going to compare this length to A. Now, the height of the triangle is 750, the big one. Well, I know the height of this triangle is what? Well, it's going to be what? Well, I know the total height is 750. Okay? And I know the depth here, right, is going to be what? if I want this one here, how are we going to do that? Well, this side here is what? It's going to be the 750 minus whatever this piece is. And what's that piece? It's going to be the depth plus 10. But that's just going to give us x. Right? Because we're measuring, see, that's the reason why we're measuring from the x-axis. So this is x equal to 0. So the distance from here to here is x, right? So the distance from here to here is going to be 750 minus x. Okay, so now let's set up our proportion. So we know that this is 750 minus x. So we get, well, we can do this, right? So we get 750 minus x goes with what? Goes with 750 is equal to a over 250. And so that tells us that a is going to equal 250 times 750 minus x over 750. Okay? So far so good? So now, what do we get here? So let's simplify this thing. So we get a equals, this is going to simplify to 1/3, right? So this is going to be 750 minus x over 3. Well, 1/3 of 750 is, we just saw, is 250. So this is going to be 250 minus x over 3. Oops. So 250 minus x over 3 is a. So that's this piece right here. Now, I've got two sides though. So this is also a. So the width is going to be what? Let me use, so the width is then going to be what? It's going to be the 750 in the middle, right? We know that's constant. It's going to be 750 plus 2 times a. So that means it's going to be 750 plus 2 times this, which is 250 minus x over 3. And so now let's simplify this. This is 750 plus 500 minus 2x over 3. And guess what? We get 1250 minus 2x over 3. So we get the top base. Okay. So that is, so basically look what we just figured out. Just so you guys know. This width, it's a function of x, but notice what is it doing? the width starts at 1250, and then it's going down by a rate of 2/3 of a foot, because X is measured in feet. So this is decreasing at a rate of 2/3. So this is the slope, or the rate of change in the width, right? So I just thought that was interesting. Okay, so now we're ready to put this all together. So it's in feet, so we know that our force is going to be equal to the integral. Now here's another thing. What are the limits of our integration? Well, the water doesn't go from here to the top. It goes from here, right, to here. So, and we know that the depth of the water is 530 feet. Okay, we know the depth is 530 feet based on our diagram. And so the maximum depth of Mead is 530 feet. And so 530 feet goes from here to here. Okay, so now, but we're integrating from where? Well, our X value here. This is our X value. So X starts at 0. So we're going from X equals 0 to what? To 540. Okay? But the depth doesn't start at 0. The water starts at 10. So we're going to go from 10 to 540. Okay? So we're going to go from X equals 10 to 540. Okay, so that's how you have to read that. Okay? So now, let's put it together. So we've got our rho, which is the weight density of water. We've got S of X times W of X dx. And so now let's plug it in. So this means that we're going to do the integral from 10 to 540. And rho, okay, so the weight density of water with feet is going to be 62.4. Oh, I keep messing that up. Yeah, that's right, 62.4. And S of X is this, X minus 10. The width of the dam is this. Oops, so let me erase some of this. So it's going to be 1250 minus 2x over 3 dx. And now, this is where I simplify. So let's simplify this thing before we integrate. So this is 10 to 540. Okay, so this is going to be 62.4. And so now, what do we want to do? Let's distribute. So this is going to be 1250x minus 2x squared over 3. And it's going to be minus 12,500 plus 20x over 3 dx. Okay, so all I did was use the FOIL method and I distributed. Okay, so let's just make sure we're on the right track here. Okay. Okay, so now simplify this further. So what do we get? Okay, so what do we get? So this gives us 10 to 540. So hold on a second, I'm missing. Oh, that's right. Okay, so here is so if -62.4. And so we just have to simplify this. So if we if we add this one here, so we've got 1250x. Let's pull out a 2/3. So if we pull out a 2/3, then this is going to become what? Let me get my calculator. I don't have my calculator. Okay. So this will become x squared, right? Because if we pull out the 2/3 here, that's going to become x squared. Oh, actually, you know what? I want to pull out the negative. I want positive. So let's pull out negative 2/3. So we'll put a negative 2/3 out. So that'll become positive. This will become positive. That'll become negative. So and this will become negative. So I don't want to start the leading term with a negative number. So if we pull out the 2/3, this will become x squared minus 2010x plus 253,125. That's this one. Okay, now, almost done. We're just about at the finish line. So now what I'm going to do is integrate this. So I'm going to pull this out of the integral. So the force now equals negative 62.4 times 2/3. And then we're going to do the integral from 10 to 540. And we get x squared minus 2010x plus 253,125. Yeah, that's it. So now we're going to integrate this thing. And so this is going to equal negative 62.4 times 2/3. And so this is going to equal 1/3 x cubed minus 1005 x squared, right? Yep. And then plus 253,125x. And then we're going to evaluate this from 10 to 540. Now, this is where you're going to use your calculator. So use your calculator. This is approximately what we get. So that's approximately 5 billion pounds of hydrostatic force. And that's it. You have a great day. Oh, hold on a second. Nope, I got another one. Here we go. Here's one for you guys. So, similar situation. So when the reservoir is at its average level, the surface of the water is about 50 feet below where it should be. Oh, hold on a second. I messed up. I looked at the wrong number here. Oh, yep, these are wrong. Sorry, hold on. These numbers are wrong. This is 1885. That's what that should be. 1885. And this should be 18750. That's what that should be. Yeah, sorry about that. I looked at the wrong, there's two parts to the problem. And so again, I don't have my calculator, so I'm doing most of the integration by hand, but the actual calculations, I'm just trusting the book. So I looked at the wrong part. So let me redo this. Everything is correct, it's just that I have to change these numbers. So this would be negative 62.4 and 2/3, and then this would be, this is going to be, again, it's going to be 1/3 x cubed minus, this is going to be half, so that'll be 9, x squared plus 18,750x from 10 to 540. And I think that's what they have. Let me double check. Right, and so what they end up getting is a little bit different. So the answer is approximately 8.8 billion. Pounds. So approximately 8.8 billion pounds of hydrostatic force. Okay, sorry about that. I got mixed up with the numbers just because I was looking in the textbook. But all the procedure and everything I did is correct. I just messed up on a couple of those numbers. So again, just rewind, rewatch it. And if you have any questions, feel free to reach out to me and ask. Okay, but do the example. Oh, that's right, I was in the middle of the example. So here's the example I want you to try. So it says when the reservoir is at its average level, the surface of the water is about 50 feet below where it would be if the reservoir was full. So let me read that again. When the reservoir is at its average level, the surface of the water is about 50 feet below where it would be if the reservoir were full. What is the force on the face of the dam under these circumstances? So we're now, instead of being 10 feet below the top of the dam, now we're subtracting another 50 feet below that. So we're going to end up at 60 feet below the top of the dam. So that's what you need to use. Okay, again, if you have any questions, reach out to me. I'd be more than happy to help you. Have a great day.